I know.
That would be really responsible of me. All right, sampling distribution. What is that? The distribution of values taken from a statistic. Please focus. I don't know why I would expect it now. Okay, now let's just pause there. Distribution of values taken from a statistic. So something like mean, proportion, IQR, range, many possibilities there for statistics. In all possible, underline all possible samples of the same size in a population. Okay. I want you to picture like a dot plot for that, or like a histogram, something like that. We're gonna make one with our M&M data today that you have on your table. And we're also gonna play with two kind of hypothetical ones before that. Because I want to show you what it would be like if you had the whole population. So, for example, John and Carol have 4 grown sons. Their heights in inches are 71, 75, 72, and 68. Okay, this is the whole population of John and Carol's sons. Does that make sense? Okay. John and Carol have 4 grown sons. Their heights in inches are 71, 75, 72, and 68. This is the full population of that. Why would you do a sample when you know all of the people and they're right there and you measured them? This is just kind of a hypothetical situation. Okay, so list all possible samples of size 2, calculate the mean of each sample, and use a dot plot to create the sampling distribution of the sample means. Okay, everyone hates this part, so you have to list all possible samples. So we could have the 71-inch guy and the 75-inch guy. And we could have the 71-inch guy and the 72-inch guy. And we could have the 71-inch guy and the 68-inch guy. Do you see what I'm doing? Okay. And then we could have the 75-inch guy with the 72-inch guy and the 75-inch guy with the 68-inch guy. And then we could have the 72-inch guy and the 68-inch guy. Okay. Does that make sense? Okay. Now, we're going to find all of the sample means just by looking at them. So this one would be 73.5, 71.5, 69.5, 73.5. No. 70. I did this one wrong though. Hmm, must be Monday. 5, 71.5. Should I use a calculator? Yeah. And then 70. Okay, do we agree that this is all possible sample means? Okay, so now we're gonna create a dot plot over here, so 69, 70, 71. So 73, 71.5, 69.5, 73.5, 71.5, 70. They're like, okay, what's the big deal? I want you to think about all of the squishmallows in the whole world. Okay, why did I pick squishmallows? Well, because I love that. Okay, now, I want you to imagine Mrs. Talbot has wings, and she also has a blindfold on. Okay, and she flies through the world and picks a random sample of 5 squishmallows. And then I measure them, right? And I take the sample mean. Okay, and then, so that's one of these. And then I fly again throughout the world and take another sample of that. And average their sushi width. And then I fly around the world and take another sample. Do you see how difficult that would be?
Yeah.
Okay, so this seems extremely easy because the population was only 4 things.
Yeah.
But I wanted you to see what a sampling distribution is. It's all possible values of a particular statistic. We're gonna do a different statistic next. So you have all possible samples. Sounds really complicated. Calculate statistics. Graph it.
Size or size?
Guys, sorry.
Bracelet.
Okay. So does it make sense, guys? Does it make sense to you that the list is gonna be the same? Hello?
Yeah.
Okay, so you could have the 71, 75, 71, 72. I'm just copying off of my previous work. Okay, so just remember, range is max minus min. It makes sense to you that you could calculate basically any statistic for these samples. So you could do sample size of 3, sample size of 4 wouldn't be that interesting, so it would just be the same each time, so this one. But you could do anything, really, just the min, the max, IQR, whatever, okay? So, this all possible samples, which is really hard if you have all the squishmallows in the world.
Yeah.
Um, calculate a statistic for each one and graph them all on a dot plot. Okay, now you're thinking to yourself, hopefully, what if Mrs. Talbot asked me to do this for a really gigantical situation? I'm not going to. The whole point of this is something I like to call backwards stats magic. Okay, the goal really isn't to get a sampling distribution and make decisions. The goal is really to be able to get some samples and work backwards to figure out stuff about the population. So picturing Mrs. Talbot flying around the world, picking 5 squishmallows and getting an average size, I'm hoping to use that to predict the average size of squishmallows everywhere. Because I'm lazy and I don't really want to find all the squishmallows everywhere. I just want to find a sample of squishmallows and kind of use it to estimate backwards stats magic. That's the whole point of stats, really, is to take a sample and use that in a lazy fashion to make decisions about the whole population. That's the whole reason we're in the class. That's the whole reason we're here, because we're lazy and we don't want to count all the squishmallows and measure them. Yeah, this class should be called like lazy statistics, but instead it's statistics. So how can I do the least and still make a decision is the question. Okay, now what I want you to think about next is the population of plain M&Ms in the world. Just think about it. They do all taste the same. You're thinking of Skittles.
I think it's really, yeah, mine, that's the example. How is it gonna work?
I said I'm going to provide you with a new back page to your packet very soon that you can staple on. It really is my fault though. They came off the printer and I was like, duh. I was so mad though. I was partially mad and partially couldn't believe that hadn't happened before. That the back page, I didn't, yeah, no, it's just. I feel like I could make a tree diagram out of that, but I'm not going to. Okay, guys, guys, before we start, breaking this stuff up, I need you to take a sample and actually verify that you have 20 M&Ms in there, because I counted these and I was half asleep this morning. So if you could, count them out, don't eat them, but you can eat them later, just don't eat them yet. Count them out like on your paper somewhere. You're probably gonna wanna separate them by color. Just make sure that you actually have 20. And does anybody not have 20?
Yes. Yeah, so go on, no. Wait, Grace, great. The old college. Understand about. Zach Ryan. You did. So friendly. We get it. Like, that's weird.
Okay. All right. Okay, here we go. State the population, parameter, sample, and statistic in your sample of 20 candies. This is a vocab question. Okay. What is the population? All M&Ms. All M&Ms everywhere in the whole world. Just think about how many plain M&Ms there are. Do you think it would be possible for us to make a sampling distribution? No, absolutely not. No. Okay. The parameter is P equals the true proportion blue candies in all M&Ms. This is what we're trying to find out. What is the true proportion of blue candies in all M&Ms? So what's the claim? Yeah, 25%. I'm just gonna put that off to the side. The claim from the company is that P equals 0.25. We're suspect of that, so we're going to do our own investigation. Okay. The sample is N equals 20 candies. Randomly selected, and you can kind of put quotations around that if you want, because I just dump them into the cups. I think that's kind of random. Yeah. And then statistic, this might be new. P hat. Okay, so let's go over this vocab. The really nice thing about this vocab, I think I've said it before, the P's go together and the F's go together. Population goes with parameter, and sample goes with statistic. Population is what you're trying to find out stuff about. That's what you're trying to predict or estimate. We're never gonna know the true proportion of blue candies of all M&Ms. We're just not in our lifetimes. And we could probably spend the rest of our life studying it, but unfortunately they get consumed as fast as they get created, so we'd never know. Just one of life's things you're gonna have to let go of. Okay. The parameter is regular P. And then the sample is the 20 candies in your little cup, randomly selected. And the statistic, so remember the hat means estimated. So P predicted, P estimated the proportion of blue candies in your sample. Okay, so the hat means sample. Okay. Now we're gonna make a graph. So create a graph of the population distribution. Okay, so we're gonna put blue, what order were they in? Blue, orange, green. I don't really know what it is about me that makes people treat me this way. Do you know what it is? Hmm. Okay, most of the time you're not going to be able to make a graph of the population distribution. Most of the time you're not going to know. We have a claim from the company this time though, so we can estimate it with the claim. Blue said it was 25%, correct? So 25% blue, 25% orange. And then all the rest are 12.5. Can you read the printed thing? Just gonna color in the blue one because that's what we're interested in today. Okay, now everyone in the class is gonna have a different sample distribution. You're going to have to calculate your proportion out of 20. You guys know how to do this? So take the number of your color divided by 20. All of it. Okay, while you're doing this, I'm gonna bring you a Post-it flag and a Post-it for your table. Post-it flags for each of you for this page in your notebook. And then I'm gonna give you one Post-it from table.
Was it bad? I had 5%. What you said, okay. Is it good?
Yeah.
Why are we talking about?
Because I want to refer back to it. in the
Oh. 5%.
Okay, I gave you, excuse me, I gave you two things. First thing I want you to do is Post-it flag this page in your notebook. Just because I want to refer back to it because I want to talk about what sampling distributions are all through the chapter and I want to flip back easily. Second thing I want you to do, take the blue Post-it and I want you to write the percentage of blue for each person in your group. Just the blue. That's why I gave you a blue Post-it.
What are names?
Just the percents. I don't need names.
What's the name, Mark? Okay, you like going on hikes?
Oh, we did, you guys hikes. I know you go down there.
Okay, once you get your Post-it ready for me, write this and then you can eat the M&Ms. They're done. Yeah. As soon as your Post-it is situated.
I want to have it for my neighbor. One thing. You good?
They're supposed to be in the thing. Oh my gosh, I missed a Post-it note. Terrible. Anybody have above 70% blue? You like blue that much?
Just like that.
Why? The camera hate me. Okay, here we go. Okay. Man, I made this way too big. I wasn't sure. You just never know. What? Oh, no, no. Okay, that's it. Why? Why, Mrs. Selby? 55% blue.
I'm not one of them.
A lot of blue.
Probably one of the early couple.
Yeah, if you could get them into the thing, not throwing them would be awesome. That'd be cool. Does that help? Okay. So you guys could take whatever this is that you have going on and not bring it back tomorrow, that'd be awesome. So first thing I need to know is the key hat. Hat means sample. So each one of these represents one of your little cups of M&Ms. I'm hoping that by having this, when we flip back to this, I can see like what the sampling distribution, and you guys could be like, oh, so if I had infinite Dixie cups with infinite different samples, size 20, and I graphed them all infinitely for the rest of my life, plus all the lifetimes after that, that's what the exact sampling distribution would be. The problem with M&Ms, as I said, they're consumable, so they're like impossible. Okay, it's impossible to get the actual sampling distribution. So what we do is we get the approximate sampling distribution with just the 30 samples that we've got in our class. And you would be surprised, I'm going to show you all through the chapter, the different things you can decide just off of a few samples. You don't have to have everything. Okay, so E, explain what your p hat dot on the sampling distribution represents. Okay, so your dot represents the proportion of blue candies in one sample of size 20. And if you know which dot is yours, you could make a little smiley arrow at it. Okay, last thing. Okay, so how are we gonna figure this out? We're gonna go back up to the dot plot. We're to count everything that's 0.25 or less. Okay, so this would be 1, 5, 5, 3, 7. Those are all the ones that's 0.25 or less, right? Okay, so we're gonna write this in proper random variable notation. Probability that p hat is less than or equal to 0.25 is 1021 out of 30 samples that we did today, which is what? 0 points. Oh, I should know that. Should we be surprised if 70% of the samples were below or equal to 25%, that we got a sample that was 25% or less? No.